Today we are going to talk about order of operations and talk about additive law of exponents. And I'm kind of going to keep pushing this, that even if this stuff feels like, yeah, I know this, try to take a second look at it, because I'm going to do my best to present all of this from a perspective of trying to dig in a little bit more to the why, rather than just memorize some rules. So in terms of the order of operations, my why statement, I'll be real, is because some old dead white guy mathematicians decided, right? Like literally a group of people gathered and decided we're all going to use the same notation for consistency. We're all going to say that these things happen in a certain order, and we need to decide what that looks like. So this is a notation thing. This part is something that we really do have to memorize. Now, your calculator, whether it's your phone or a scientific calculator or a graphing calculator, also follows an order of operations. Sometimes people use the acronym PEMDAS. Which is parentheses, exponents, multiplication, and division, and then addition, subtraction. In terms of like numerical computational accuracy, if mistakes are going to be made, usually those mistakes are happening because of an order of operations thing. And the one that trips people up the most is definitely parentheses, because sometimes parentheses and multiplication are implied, but sort of not explicitly written. So let's just dive into a couple of examples. So if I had something like 5 times 3x plus 2 minus 4 x minus 1. I should have started by saying that my least favorite mathematical instruction for a problem is the word simplify. Because simplify means a whole heck of a lot of different things, and it doesn't really tell us what to do. For something like this, if our instruction is to simplify, then what that means is that our goal is to not have parentheses anymore and to have combined any terms that we're able to combine together. So when I look at this and I'm thinking through the order of operations, parentheses come up first. So we've got parentheses in here. And what dealing with parentheses means is actually two things. One, is there anything that I can combine inside of the parentheses? And the way that I wrote these, the answer to that question is no. My next thing with parentheses is to think about, is there something that I need to distribute into those parentheses? And in this case, yeah, I've got 2 places to distribute in. I will just point out super common visual mistake that students make, not just students, people every day. It's really easy for your brain to see this -4 and +2 and simplify that to be a -2. Just kind of be on the lookout for that. The problem is that there's invisible multiplication in here between the number and those parentheses. And if it helps, write in that multiplication. Because in terms of the order of operations, we have to deal with the multiplication first before we're dealing with addition and subtraction. So I'm going to go ahead and distribute that 5 through, which means this statement says 5 is multiplied by the 3x and by the plus 2. So I'm looking at 5 times 3x plus 5 times 2. This minus 4 is kind of hanging out by itself at the moment, but that 2 has multiplication into that x minus 2. 2 times 1. Now I can simplify stuff further. I've got 15x plus 10 minus 4 plus 2x minus 2. Now we talk about, oh, and you all let me know if stuff isn't big enough and I'll zoom in a little bit. So we talk about combining like terms. I don't know who came up with that phrase, but what it means by combining like terms, we're grouping things into stuff that are numbers. Those are alike. So stuff that's numbers, we're going to group that together. Looking at this, I've got a 10, a -4, a -2, and combining like terms would mean I should do whatever operations I need to with addition and subtraction to make that work out. So 10 minus 4, I'm at 6, minus 2, I'm at 4. So I've got a positive 4, and then that 15x and the 2x, those terms are alike because they both contain an x to an invisible power of 1. So 15x plus 2x is 17x. So if the instructions are to simplify, that's really my final answer. Every algebra textbook out there uses this lovely symbol for division. No one in a calculus class is writing that little thing. When we're talking division, we're either using a slanted line like this or a horizontal line to make something a fraction. But this symbol is convenient to type into a textbook because it helps you to keep everything on one line. And I'm 100% sure that that's why we use that symbol and continue to use that symbol in algebra books, even though it's not really something that you would use in calculus. But just in terms of order of operations, if I were to write something like 12 divided by 3, also, we tend to ditch the x for multiplication and replace it with a dot in calculus because we use x as a variable so often. We don't want it to get confused with multiplication. So let's say that I had something like that. I mean, that might actually be something that you would do if you were typing this into a calculator. But in terms of the order of operations, we don't have any parentheses, though we could rewrite this to have parentheses. It doesn't currently have parentheses. We don't have any exponents on it. So I'm looking to deal with the multiplication and division first. Typically, we move from left to right just because in English we read from left to right. I really think about this as sort of regrouping it. So I have division here. So I'm going to go ahead and deal with this. 12 divided by 3, I'm looking at 4. I move over here and we have addition and I have multiplication. So I have to deal with the multiplication first. 1 times 5 is 5. Now I'll put that plus back in. I'm subtracting something. I've got division again over here. So I'm going to deal with that division first. Combining all of that stuff together, Now, here's where life gets fun. The textbook is going to tell you that you should move from left to right. If I'm not using a calculator, I am not moving from left to right, because I would much rather deal with the 5 minus 25 first. Be smart about the calculations. I don't know whether I mentioned this on Wednesday. UC Davis is a non-calculator campus for pre-calculus and calculus classes. So when you are taking exams, when you're taking quizzes, you won't be using a calculator. Now that also means that the numbers tend to stay pretty simple and that there isn't a huge expectation that you're like really simplifying numbers and stuff. But this I would expect you to simplify because the numbers are fairly nice. So I would look at this and say, well, 5 minus 25, I've got way more of the negative stuff than the positive stuff. My result's going to be negative. 5 minus 25 is going to be negative 20. And I would do this as negative 20 and then add the 4 to end up with negative 16. Sorry, I know that went off a little. Order of operations is something that's just going to keep coming up and infiltrate lots of things that we do. I'm not going to spend more time on it today. I just wanted to at least like refresh everybody's memory that it's there, it exists. But I really want to dive in and talk a little bit about exponents because they're everywhere. And I just want to take a step back and specifically talk about the additive law of exponents for a minute, because I know that for me, this is not something that I was ever taught in high school. And it's one of those things that really gets at the why we have to do things the way we do with exponents. And I want to start just by asking, so take a second to think about it, but I promise not to make you talk, but stick your hand up if you know what the answer to this is. 5 raised to the 0 power. I promise not to make you talk. Keep your hand up if you're willing to talk and share a guess. Okay, I'm going to work on names. I've like had 18 months of not practicing names because I've been staring at them on a Zoom screen. So hi, I'm Sara. You are? I'm Martin. Martin? Okay. What were you thinking? Is it 1? People were also thinking 1. Did anyone have a different guess? You got a guess in the back. Hi, I'm Sara. You told me your name on Wednesday and I don't remember what you said. Amber? I thought it was 1. Oh, awesome. Cool. So we got a 1. Does anyone know why? Totally. So it's a thing that someone told you that you should go memorize, right? So today is the day we learn why. Don't take notes for a second. Don't take notes for a second. Just be present in the moment and then we'll go back to taking notes. I will post all of these notes onto Canvas, I promise. So just notation wise with exponents, if I write something like 5 raised to the 3rd power, I might read this as 5 cubed. I might read it as 5 to the 3rd. There are different ways we can say that, but this means in its expanded form that I'm multiplying 5 by itself 3 times. 5 times 5 times 5. So what the additive law of exponents really at its heart is saying, well, this was just a shortcut notation for something. So if I had 5 raised to the 3rd power times 5 raised to the 4th power, well, I can expand each of these out. So that 5 to the third says 5 times 5 times 5. And the 5 to the fourth says 5 times 5 times 5 times 5, which means we're multiplying those things together. In total, I have 7 of those 5s. And that shortcut way, right, is to write that as 5 to the 7th. And we can get there by doing 5 to the 3 plus 4. That's called the additive law of exponents. We don't really have a choice about it. It's not like there's a rule that says if I'm multiplying two things with the same base, I add the exponents. Okay, actually, that is the rule. But this is the why. The why is because if we put them in their expanded form, this is what happens. So now comes the fun with the 0. Oh, by the way, that same group of old dead white guy mathematicians, no, I don't know that it was the same group. I'm just saying things. They agreed that they wanted this additive law of exponents to work. So if we decide that we want that additive law of exponents to work, then we don't have a choice for what some of these other things mean. So if I write, for example, 5 to the 0 times 5 squared, that's how I read it, or 5 raised to the second power, or 5 to the second. The additive law of exponents says this has to be 5 to the 0 plus 2. Well, if I'm not sure what this part is, I do know what 5 to the second is. That's 5 times 5, or 25. I know what 0 plus 2 is, which means I also have a 5 to the second over here, which means I also have a 25. We don't have a choice. There's only one thing that can go in that box. It has to be a 1. 5 to the 0 has no choice but to be equal to 1. Now, no matter what base you put in there, this same kind of thing is going to happen, right? If I had 7 to the 0 times 7 to the 1, that's going to be 7 to the 0 plus 1. If I wasn't sure what was going in this box, that's a 7, and that is also a 7. What times 7 equals 7? Yeah, we don't have a choice. 7 to the 0 must be equal to 1. So in general, when I have a number raised to the 0 power, that's equal to 1. When A is an element, I'm using fancy notation for a second. I can read this as A is an element of the real numbers. You'll see that in the textbook in a few places. Okay, I'm going to pause in case anybody has questions and or if you want to catch up in your notes. Good times. I'm going to return to this additive law of exponents at different times throughout the quarter. But I do want to do one more thing with the additive law of exponents first. So now that we know what 5 to the 0 or 7 to the 0 has to be equal to, that means we can also talk about what negative exponents have to be equal to. We don't get a choice. If we're accepting that the additive law of exponents has to work, then if I write something like 5 raised to the first power times 5 raised to the negative first power, then that additive law of exponents says, I have two things with the same base. I know that my shortcut is to add those exponents together. Well, 1 plus negative 1 is going to give me 5 to the 0. Now over here on the left-hand side, 5 raised to the first power, that's a 5. And if I'm not sure what goes in this lovely box, I'm just going to keep working through this. So 5 times something, and now we know that 5 to the 0 must be equal to 1. Well, I don't get a choice. The only thing in that box that makes this true is if 5 to the negative 1 is equal to 1/5. In general, for a lot of the math that you will encounter on your journey through math at UC Davis, it's actually a very, very small number of rules that some folks agreed upon. But all of those rules have consequences that kind of spill out, right? So here's one of those things where agreed upon the additive law of exponents, and now because of that, there are consequences. There's no choice about what 5 to the 0 is equal to, and there's no choice about what 5 to the negative 1 is equal to. This works no matter what number we pick over here, right? If I had 3 to the first times 3 to the negative 1, that's equal to 3 to the 1 plus negative 1. 3 to the first power is 3. If I wasn't sure what goes in this box, 1 plus negative 1 is 0. 3 times something is supposed to be equal to 1. Well, that something is equal to 1/3. We'll return to this additive law of exponents a little later in the quarter. But for now, I want to get some more practice with some messy order of operations kinds of things. Or we can take a little pause and have some fun with fractions. So let me get a vote. And if you're on Zoom, you can type your vote in the chat as well. More PEMDAS stuff or fun with fractions? Some people vote fun with fractions. Some people vote order of operations practice. Now here's the real question. Are we just avoiding fractions or we want more practice with order of operations? I heard a mix of both. I heard a mix of both. Avoiding, you know what, online, all of our Zoom folks want to do fractions. So I'll mix it up. Let's do both. A few words about fractions. And like this is something, again, that's going to be sort of a running theme throughout the class, talking about fractions. But I'm diving into a bunch of these things today just because they're mechanically, these are calculation tools that we're going to need throughout the quarter. So some unfortunate notation things when it comes to fractions. Oh, wait, no, I said fun with fractions. We got to talk fun with fractions first. So don't put this part in your notes. You'll look at it later and go, I don't know what that was anyway. Let's say that I know I said fun. I'm trying to make this fun. So this is a candy bar, kind of fun. And it's like a Hershey's bar. People like s'mores, have the little rectangles in the Hershey's bar. So I have this Hershey's bar, and I probably should have looked at one to see. I don't really know. I'm going to pretend that it's got 1, 2, 3, 4, 5, 6, 14 of those little pieces, right? But so that would be like a whole Hershey's bar. But it's like the end of a night of making s'mores. Oh, I'm saying s'mores. Do people know what s'mores are? I grew up in a camping family. So like you got your graham cracker and you toast a marshmallow and you throw some chocolate on there. Or if you're at Starbucks, they give you a pump of the marshmallow stuff and a pump of the chocolate syrup. And then they sprinkle something on top that's supposed to taste like graham crackers. So it's the end of a night of making s'mores. And what's lying around was like a piece that's shaped like this, and a piece that's shaped like this, and a chunk that was kind of like this. And someone was like, oh, hey, is that a whole Hershey's bar? And my response is, well, maybe, but those are not all the same size pieces. And if I'm going to try to figure out how much of this Hershey's bar I have, I need to be able to look at all of these with the same size pieces. So then I look carefully and I'm like, oh, well, that one was really like that. And this one really looked like this. And this one looked like this. Well, now if they all have the same size pieces, then I've got 4/14 and 2/14 and 6/14. And now I'm in a better position to say, was that a whole Hershey's bar? I got some head shaking, no. And I would agree. The answer is no. Because if I put all of these together, now that they're all the same size piece, I have 12/14 of a Hershey's bar, but a whole Hershey's bar was 14/14. Probably my son. Or the dog. The dog really likes chocolate. She shouldn't have chocolate, but if they fell on the ground, my dog definitely found them. So bottom line, the denominator of a fraction means something. The denominator of a fraction tells me how big the piece is. And the numerator says, this is how many of them I have. Okay, no one's really talking Hershey's bars in the textbook. So this part you can take notes on. Now we're doing stuff with actual numbers. So a couple things. I don't normally I don't really care what anyone's handwriting looks like as long as it's readable to me. And my son's handwriting is terrible. I can read some pretty terrible handwriting. But what I will say, this is something that you should figure out for yourself. What you need to do to make sense of what you have written. So right now, I have written 2/3 times 5. Now what this means is that the size of these pieces were 1/3, and I have 2 of them. But that times 5 says I actually have a total of 5 of those 2/3. This is equivalent to saying 2/3 plus 2/3 plus 2/3 plus 2/3 plus 2/3. The denominator is the size of the piece. I'm not like shrinking or growing the pieces. The size of the piece is thirds. And I have a total of 10 of them. Visually, one, I don't expect anyone to write that out. Like, that's a waste of time. I'm doing it to illustrate a point. If you write 2/3 times 5, or if you write 2/3 times 5, or if you write 2/3 times 5, or if you write 2/3 times 5, there's a subtle difference in the height and the size of each of those numbers. And if you're moving through a problem quickly, I have seen lots of students get mixed up. And I think part of it is because of the size and the height of the numbers, especially this one. This one really has a tendency to turn into 2/15. Use more paper, write bigger, invest in a small whiteboard, but don't let your handwriting be the reason that you're making math mistakes. Know that if I have a fraction times a number, that fraction times a number isn't changing my denominator because the denominator is the size of the pieces. It's just telling me I've got a total of 10 of those with a size of 1/3. I'm guessing there aren't questions, but I'm just pausing for a second in case there are questions. Watching my chat, making sure there aren't questions out there in Zoom land. Okay. My next is sort of like notation thing with fractions. And I promise we will do lots with fractions over the course of the quarter. Again, I totally can move it down. I am about to do this. Oh, let me say, let's give the instruction of multiply and express your answer in lowest terms. I'm going to give you all a second to do it because my guess is that most of you already started doing it. Would anyone like a little more time to work on it on their own? Okay. Saw people still writing, so I'm wanting to give you a chance. There are lots of correct ways to get through this problem. There are lots of correct ways to get through most math problems. I'm going to share some things that are helpful for me. But if you have correct ways that are getting you to the correct answer, go for it. I am gonna do this in like crazy slow motion. This is not actually how I would do the problem, but here is one way that you could do the problem that sort of gets at the math behind what's going on. So the first thing that I'm gonna do is what's called prime factorization. I am going to take everything and break it apart into its smallest little bits of multiplication that we could do. Again, I wouldn't actually do this to get through the problem. I'm just showing you what's going on. So over here with this fraction, that prime factorization, 9 is the multiplication of 3 times 3. And both of those are prime numbers because we can't break them down any smaller as a multiplication problem. 16 is 2 times 2 times 2 times 2. I am now going to use the associative property of, well, I don't know. Okay, there's some vocabulary in this book that unless you are a math major, really don't worry about it. Is anyone a math major? Cool. We're really not going to worry about most of the vocabulary in this book. It's never coming up in calculus. So I'm going to use what's called the associative property and also what's called the commutative property of multiplication, which means I can multiply stuff in whatever order I want. And if it's all multiplication, I can shift things around however I want. So I'm going to shift things around a little. I'm going to take this 3 and hop it in front of the 2 so that on top it looks like 3 times 2 times 3. I haven't changed the numbers and I haven't changed that I'm multiplying. I just rearranged them. In the denominator, I've got 3 times 2 times 2 times 2 times 2. Now there's a word that people might use that starts with a C that they would do next, and someone would say they're canceling. I have an issue with that. I don't like it as a word when we're talking about fractions. I don't mind if it's the word that resonates with you. But to me, cancel feels like we should get 0. And that's not what happens when we're talking about fractions. What's happening here is that 3 divided by 3 is equal to 1. And 2 divided by 2 is equal to 1. And I have a tendency when I'm canceling terms or crossing something out from the top to the bottom, I write it in as a 1. That means that on top, the one thing that's left that doesn't have a partner on the bottom that would make it a 1 equivalent is 3. And then I can remultiply these together and say 2 times 2 times 2 is 8. And I get 3/8. It would also be okay to look at the bottom and write it as 2 raised to the 3rd power. Now, part of the reason that I like doing this that I like to write in my 1s instead of like canceling is that if I had something maybe about 4/15 times 15 over 24. One of the things that I think is nice, and I'm not going to do this by, well, what the heck? I might as well prime factor it. It's not that bad. It'll be quick, sort of. Oh man, no, I'm not going to. I lied. Okay. If I'm going to simplify this, I'm going to choose to group the 15 over the other 15. and then have the 4 over, sorry, I said 4, I wrote 5, I don't know. 4 over 24. One of the reasons that I specifically like to write a 1 and not just cross things out is that this 15 over 15 turns into a 1. Now the 4 over 24, 24 is divisible by 4. It's going to leave me with a 6. That 6 goes on the bottom. But for me, writing this as a 1 helps me to remember that that what goes on top is 1. It's not that like everything is gone and suddenly we don't have a numerator. My numerator is 1, and we explicitly have to write that. Good times. We have about 8 minutes left, and I just have one more thing that I wanted to practice a little bit of today. And that is the dreaded word problem. Let's just call it out there. Here's the deal. Like, every problem has words in it. I understand what people mean when they talk about not liking word problems. Real life is word problems. Your bio classes are full of word problems. Your chemistry classes are full of word problems, right? It's just, they're just normal exercises. And one of the reasons that we throw them into math is so that you have the opportunity to practice translating words into mathy symbols so that you can do something with them. And in this very first section of the book, keeping it fairly simple, but just practicing translating some phrases into mathematical expressions. So if I said something like the difference of A and 5. Well, that word difference means subtraction. And if I were translating this, the difference of A and 5 would translate as A minus 5. The product of 4 and 6, product is multiplication. So this translates as 4 times 6. Now, I'll be honest, these are boring. This is not really what's going to come up in a problem. So let's step it up a notch. A is 3 less than twice B. It will give you all a second to translate that into mathematical symbols. I'm gonna write down the number one wrong answer that I see people put for this problem. You ready? Did anyone want to guess what the number one wrong answer is? That's okay. I've graded a lot more algebra assignments than you have. The number one wrong answer that people put is this. And I'm going to apologize for the English language or something. I don't know. This really is a grammatical issue more than a math one. But this phrase, 3 less, specifically than, the than part means that the 3 is being subtracted from something. So that's our wrong answer. I'll go ahead and get rid of it. The twice b part does mean 2 times b, but 3 less than 2 times b means I'm subtracting 3 after I deal with the twice b. And that is for sure the number one wrong answer that I see.